In this lesson, I'll show you how to write a conservation of energy statement for a rotating system. The question reads, a solid sphere of mass 2.0 kilograms and a radius of 0.3 meters is constrained to rotate about a vertical axis passing through the center of the sphere. Take a look at this illustration to get an idea. A cord is wrapped around what would be the equator, passes over a pulley of negligible mass, and is attached to a mass of 0.8 kilograms that is allowed to fall 1.0 meters under the influence of gravity. In the first part of this question, we are expected to write a conservation of energy statement for the system, and then in part B, we'll learn how to find the velocity of the hanging mass and the angular momentum of the sphere. So let's begin with A. We have this mass that is hanging from this pulley and is wrapped around the sphere, and this sphere rotates about its vertical axis, so assume that it is rotating like this, and in the process this mass falls. Now because this mass is hanging, it holds potential energy. And the formula for potential energy is listed right underneath here, where it can be found by taking the mass of the object multiplied to the acceleration due to gravity represented by g times the height in which it falls. So the potential energy that it holds will go into two things. It will go into the kinetic energy as it falls down, and it will go into the kinetic energy required to rotate this sphere. Now there are two types of kinetic energies that we're dealing with here. There's the linear kinetic energy, which is represented by this formula, mass times velocity to the power of 2 over 2, and we have rotational kinetic energy, which takes into account the moment of inertia and the angular velocity represented by omega. So how do we put this all together? Well, because we know that the potential energy will go into those two things, we can write down that potential energy is equal to, or it goes into, the linear kinetic energy plus the kinetic energy required to rotate the sphere, which is represented by, again, Ke for kinetic energy sub r, representing the rotational. So for potential energy, we have mgh. I will write down mgh, and because this mass is represented by the capital letter M, I'll replace this lowercase m with the capital M. Eventually I will replace g with 9.8 and all the other values, but here they're only asking for the statement. The formula for kinetic energy, so the expression that I'll replace in for this, is right here, mv to the power of 2 over 2. And again, I'll change this little case m with the capital, because we're talking about the kinetic energy of the mass, plus the rotational energy of this. The rotational kinetic energy is represented by that formula. Now let's continue with this. The moment of inertia for a sphere, a rotating sphere, has its own formula. It's 2 over 5 times m times r to the power of 2. So I will be replacing that with this expression, and I'll also be replacing omega with v over r. So that will be v over r. Let's go ahead and do that. 2 over 5 little case m r to the power of 2. Notice that I chose little case m because the mass of the sphere is represented by that little case m. So you want to make sure that you don't confuse the two types of masses. Of course, it'll become more clear once we substitute all those values. And you see this part right here? That will be replaced with v over r, and it's being squared, so both of these are being squared, and all of that is being divided by 2. This 2 right here. Let's cancel some of these out. So this r squared and this r squared will cancel out. This 2 and that 2 will cancel out. Let's clean this up. mgh is equal to capital M v to the power of 2 over 2. And here we have plus mv to the power of 2 over 5. As you can see, we have a factor v to the power of 2 common, so I can factor that out. That's the right side, and the left side remains the way it is. At this point, we can actually substitute all of the values in for their respective letter, and I think that would be a good idea given that for b they want the actual velocity and the angular momentum. So let me substitute the solid sphere as 2 in for little m. It's 2 meters, and of course you should be writing the units down, but for the sake of simplicity I will not. So 0.8 and 2.0. the velocity, that's what we're looking for. And the mass of the object is 0.8. The gravity is 9.8. And the height at which it drops is 1.5. So we will calculate this part and then divide both sides by what we find. So 0.8 divided by 2 plus 2.0 divided by 5. That gives us 0.8. We'll divide both sides by 0.8. So let's multiply the left side and then divide by 0.8. 0.8 times 9.8 times 1.5 divided by 0.8. And that's what we get as 14.7 is equal to v to the power of 2. Now we square root both sides. We square root and we end up with 3.8 plus minus is equal to the velocity. Of course, we're only going to take the positive version because the negative version doesn't make sense in the context of this question. We found the velocity, and now we need to find the angular momentum. The angular momentum is represented as L is equal to I for moment of inertia times the angular velocity. That shouldn't be hard. Angular velocity is v, and we found it already to be 3.8 over the radius. The radius is given as 0.3. So we'll divide those out and then multiply it by the moment of inertia was 2 over 5 times the mass of the sphere. That's 2.0. And the radius of the sphere is 0.3 to the power of 2. So this gets multiplied to that. Let's see what happens. 2 over 5 times 2 times 0.3 to the power of 2 times 3.8 over 0.3. And we end up with an angular momentum of 0.912. Of course, it would help if you had used the units because we can kind of determine what the final units are for angular momentum. But from past experience, we know that angular momentum has the units kilograms times meters squared per second. We found the answers to both A and B, and that is how to write a conservation of energy statement for a rotating system and to help us find important values like the velocity and angular momentum.